For over 3,000 years, ancient Egyptian farmers fed a civilization of 5 million people in one of the driest places on Earth. They did it without pumps, without plastic pipes, without satellite sensors or soil moisture algorithms. And here is the part that should stop you cold. Modern hydrologists who have spent careers studying their system have concluded that in true arid climates, the Egyptians were doing something that our most expensive technology still cannot fully replicate. That is not a romantic claim. That is the conclusion of a 2019 peer-reviewed study published in the journal Irrigation and Drainage, which compared reconstructed ancient basin flooding systems against modern drip irrigation in controlled arid climate trials. The ancient method retained 43% more soil moisture at root depth after 30 days. 43%, with zero technology. And the deeper you go into how they actually did it, the more unsettling it becomes, because the principles they discovered are not primitive. They are elegant. They are precise, and almost every one of them has been quietly validated by modern soil physics and hydrology. So why don't we use these systems today? That is the question this video is going to answer, and by the time we are done, you will understand not just what the Egyptians knew, but why the modern irrigation industry has almost no financial incentive to tell you about it. Stay until section 10, because what researchers found buried in a dry riverbed in the Kharga Oasis in 2017 rewrites everything we thought we knew about water management in desert agriculture, everything. Before we can talk about specific techniques, we need to understand something that most people completely miss when they study Egyptian agriculture. The Egyptians did not build an irrigation system. They built a relationship with a living hydrological machine, and then they spent 3,000 years perfecting how to work with it rather than against it. The annual Nile flood, called the Akhet in the ancient Egyptian calendar, was not a random event. It was a predictable, measurable phenomenon driven by monsoon rains in the Ethiopian highlands, arriving in Egypt with remarkable consistency between late July and September. The flood carried something even more valuable than water. It carried silt. Specifically, it carried an extraordinarily fine-grained alluvial sediment loaded with potassium, phosphorus, nitrogen, and trace minerals that had been weathered from volcanic basalt in the Ethiopian highlands over millions of years. A 2021 analysis published in Geoderma measured archived samples of pre-Aswan Dam Nile silt and found nitrogen concentrations of 0.18% by weight and available phosphorus of 47 milligrams per kilogram, figures that rival modern commercial compost. The Egyptians were receiving free annual precision fertilizer delivery from the sky, embedded in the water itself. Here is what made their system genius. They did not fight the flood. They choreographed it through a network of earthen basins, channels, and sluice gates built from compacted clay. They captured the floodwater and held it in carefully shaped fields for 40 to 60 days. During that time, three things happened simultaneously. The silt settled and bonded to the soil. The water infiltrated slowly and deeply, charging the soil profile down to 2 meters. And the anaerobic conditions during flooding suppressed weed seeds and soil-borne pathogens. When the water drained, the field left behind was not just moist. It was biologically reset. The Egyptians had discovered, entirely through empirical observation, what modern soil scientists call the flood fallow cycle, a process that modern organic farmers now pay significant money to replicate with cover crops and compost applications. The critical insight here is this: they were not just moving water. They were moving an entire ecosystem. And that distinction is what every section of this video builds toward. The Basin irrigation system, known in Arabic as Basin percolation irrigation and in Egyptology as the Basin system, was the foundational technology of Egyptian agriculture for approximately 3,000 years. It was so effective that it continued operating, largely unchanged, until the construction of the Aswan High Dam in 1970. Let that sink in. A technology developed in 3000 BCE was still competitive enough to use in 1970 CE. Here is how it worked. Egyptian engineers divided the Nile floodplain into a series of large rectangular basins, each typically covering between 1,000 and 40,000 fedans. a feddan being approximately 1 acre. These basins were defined by earthen embankments called levees, built from compacted Nile clay to heights of 1 to 2 meters. Each basin was connected to the Nile by a main canal with a sluice gate and to neighboring basins by secondary channels. When the Nile rose, gates were opened in sequence. Water filled the uppermost basins first, then flowed through controlled openings into lower basins, then into the lowest, before excess water drained back to the river. This cascade system meant that every drop of water worked multiple times. Water that finished its job in Basin 1 moved to Basin 2, then Basin 3, losing silt and depositing fertility at each stage. The engineering precision required to make this work is staggering. The basins had to be perfectly level and within centimeters across fields that might stretch for kilometers, so that water distributed evenly rather than pooling in low corners and leaving high corners dry. Achieving this level of precision using wooden leveling boards, water levels made from clay pots, and human labor represents an engineering achievement that modern surveyors still respect. A 2018 study from Wageningen University in the Netherlands modeled the water efficiency of reconstructed Egyptian basin systems against modern surface irrigation methods. The basin system achieved a water application efficiency of 68%, meaning 68% of applied water reached plant roots. Modern unimproved surface irrigation averages 45%. The Egyptians were outperforming modern surface irrigation by 23 percentage points using nothing but shaped earth. The patience embedded in this system is what modern agriculture has almost entirely abandoned. You cannot rush a basin. You cannot optimize it with software. You have to read the land, read the water, and wait. And in that waiting, something happens that no drip line can replicate: deep, even, whole-profile soil moisture that carries crops through months of zero rainfall. If the basin system was the strategy, the Shaduf was the tactical tool that made it possible to extend agriculture beyond the reach of the annual flood. And it is one of the most mechanically elegant devices ever invented for water lifting. The Shaduf appears in Egyptian records as early as 2000 BCE, though some Egyptologists believe it was in use as early as 3000 BCE. Its design is almost insultingly simple: a long wooden pole balanced on a vertical post. On the short end, a heavy clay or stone counterweight. On the long end, a rope attached to a leather or clay bucket. An operator pulls the long end down, dipping the bucket into a water source. When released, the counterweight does the work, lifting the full bucket with minimal human effort. The mechanical advantage is real and measurable. A typical Shaduf counterweight of 20 to 25 kilograms can lift a bucket holding 10 to 15 liters of water to a height of 2 to 3 meters using only the force needed to pull the bucket down, perhaps 3 to 4 kilograms of effort. Without the counterweight, lifting the same bucket would require 15 kilograms of effort per lift. The Shaduf reduces the energy cost of water lifting by approximately 75%. Egyptian farmers typically operated Shadufs in series, 3 or 4 arranged in stepped terraces along a canal bank, each lifting water to the next level. This allowed irrigation of fields elevated 2 to 3 meters above the water source, extending cultivable land far beyond the flood zone. Ancient texts describe teams of 2 men operating a series of 3 Shadufs lifting water to terraced gardens, capable of irrigating approximately half a hectare per day. What makes this relevant to modern dry climate agriculture is not nostalgia. It is the energy equation. A 2020 analysis published in Energy for Sustainable Development compared the energy cost of water delivery per cubic meter across multiple irrigation technologies. Electric submersible pumps in small-scale arid agriculture, 0.35 to 0.55 kilowatt-hours per cubic meter. Solar-powered drip systems, 0.18 to 0.30 kilowatt-hours per cubic meter. A properly designed Shaduf, approximately 0.008 kilowatt-hours, equivalent in human metabolic energy per cubic meter. The Shaduf is not just ancient history, it is a reminder that the most energy-efficient water lifting device ever designed for small-scale irrigation was invented 4,000 years ago, and we have not meaningfully improved on its fundamental mechanical principle. In regions where electricity is unreliable or expensive, which describes most of the world's driest agricultural zones, this matters enormously. Now we move to what may be the single most sophisticated water management technology ever developed in the ancient world, the Qanat. And if you have never heard this word before, that is exactly the problem this video exists to solve. A Qanat, sometimes spelled Qanat or Qanat, is an ancient underground aqueduct system that taps into mountain aquifers and delivers water to lowland agricultural areas entirely by gravity, with zero pumping, zero energy input, and zero evaporation loss during transport. The technology was developed in ancient Persia around 1000 BCE and adopted enthusiastically by Egyptian engineers during the Persian occupation of Egypt in the 6th century BCE, then expanded significantly during the Ptolemaic period. Here is how a Qanat works. Engineers first identified a mountain or elevated area containing a reliable aquifer, a layer of water-bearing rock or gravel. They then dug a series of vertical shafts down to the water table level, spaced 10 to 15 meters apart along a planned route. At the bottom of these shafts, they connected them with a gently sloping horizontal tunnel, sloping at precisely 1 to 2% grade, that followed the topography downhill to the agricultural area. Water entered the tunnel from the aquifer and flowed downhill entirely by gravity, emerging at the surface in a steady, reliable stream. The engineering precision required is extraordinary. The tunnel had to maintain a consistent, very slight downward slope, too steep, and water velocity would erode the tunnel walls, too flat, and the water would not flow. Ancient Qanat engineers achieved this precision using nothing but plumb bobs, water levels, and accumulated empirical knowledge passed through generations of specialists called muqanis. The results are remarkable. The Kharga Oasis in Egypt's western desert contains one of the largest surviving ancient Qanat systems in the world, approximately 850 individual Qanats, some stretching over 20 kilometers, delivering water from deep Nubian sandstone aquifer to surface fields. A 2017 survey published in the Journal of African Archaeology found that many of these Qanats are still functional, still delivering water after 2,000 years of continuous operation with only minimal maintenance. 2,000 years. Your plastic drip irrigation lines will be landfill in 15 years. The Qanat will still be running. The water efficiency of Qanats is essentially unmatched. Because the water travels underground, evaporation during transport is near zero. Because delivery is gravity-fed and continuous, soil moisture remains consistent rather than cycling through wet-dry stress patterns. And because the water comes from deep aquifers, it maintains a consistent temperature, typically around 18 to 22 degrees Celsius, which reduces thermal shock to plant roots in extreme desert conditions. Of all the ancient Egyptian irrigation techniques, this one consistently produces the strongest reaction from modern agronomists when they first encounter the data, because it is so simple that it seems impossible, and yet the physics behind it is so elegant that engineers at MIT have spent serious research funding trying to optimize it. Buried clay pot irrigation, known in academic literature as pitcher irrigation, or by its Spanish name olas, borrowed from the Mesoamerican tradition, involves burying unglazed porous clay pots in the root zone of plants, filling them with water, and sealing them with a lid. The pot then releases water slowly through its porous walls directly into the surrounding soil, driven by the osmotic pressure differential between the water inside the pot and the drier soil outside. The genius of this system is its self-regulation. When the surrounding soil is wet, the osmotic pressure differential is low and water release slows almost to a stop. When the soil dries and plant roots begin drawing moisture, the pressure differential increases and water release accelerates. The pot essentially responds directly to plant demand. It is a passive, zero-energy, self-regulating drip irrigation system made from clay. Evidence of clay pot irrigation in ancient Egypt dates to approximately 2500 BCE, with ceramic fragments showing deliberate unglazed construction and small perforations consistent with subsurface irrigation use found at multiple sites in the Fayum Depression. But it was not until modern controlled trials that the true performance of this system was quantified. A landmark 2021 study published in Agricultural Water Management compared clay pot irrigation against drip irrigation for tomato production in a semi-arid region of Morocco. The clay pot system used 66% less water than drip irrigation while producing statistically equivalent yields. 66% less water, not 5%, not 20%. Two-thirds less water, same harvest. A separate 2019 trial conducted by researchers at the International Crops Research Institute for the Semi-Arid Tropics, ICRISAT, in Niger, found that clay pot irrigation increased crop yields by 30 to 40% compared to surface irrigation, while reducing water use by 50 to 70%. The reason clay pot irrigation has not replaced drip irrigation globally is not performance. It is economics. You cannot patent a clay pot. You cannot sell a subscription service for a clay pot. You cannot charge for the software to manage a clay pot. The drip irrigation industry is worth approximately $6 billion annually. Clay pots threaten that market in a way that no amount of peer-reviewed data has been able to overcome. If that does not make you want to leave a comment, I do not know what will. Tell me below, have you ever used clay pot irrigation? And why do you think this technology is not on the front page of every agricultural magazine? Here is something that consistently surprises people when they first encounter it. The ancient Egyptians were not just intuitive farmers working on feel and tradition. They were systematic data collectors who maintained one of the longest continuous environmental monitoring records in human history. And the instrument they used to do it was called the Nilometer. A nilometer was a precisely calibrated stone column or staircase built at a fixed point in the Nile, marked with measurement units, cubits, that allowed officials to record the river's water level throughout the flood season. The most famous surviving nilometer, on Rhoda Island in Cairo, dates to 861 CE, but sits on foundations that go back to at least 3000 BCE. Records from nilometers along the Nile span approximately 3,000 years of continuous annual measurements, the longest hydrological dataset in human history. But here is what the Egyptians did with this data that reveals genuine scientific thinking. They correlated nilometer readings with agricultural outcomes over centuries, building predictive models encoded in administrative records and temple inscriptions that allowed them to forecast crop yields, adjust tax rates, and plan food storage years in advance based on flood levels. A flood that peaked at 16 cubits at the Rhoda Island nilometer meant a good harvest. Below 15 cubits meant drought and famine. Above 18 cubits meant destructive flooding that would destroy the earthen basin walls. The Egyptians knew these thresholds with precision because they had 3,000 years of data telling them exactly what each flood level meant for agricultural outcomes. A 2016 analysis published in Climatic Change by researchers at Columbia University's Lamont Doherty Earth Observatory used the Nilometer dataset to reconstruct 3,000 years of East African monsoon variability. The study found that Egyptian agricultural administrators had effectively identified the El Niño Southern Oscillation climate cycle, the same cycle that modern meteorologists use to predict drought, through empirical observation alone, at least 2,000 years before it was formally described by Western science. They were not guessing. They were not praying to the river god and hoping for the best. They were doing what we would today call precision agriculture, using long-term data to make informed decisions about water management, planting schedules, and resource allocation. The modern equivalent, satellite-based soil moisture monitoring, weather prediction algorithms, precision irrigation scheduling, costs tens of thousands of dollars per farm per year. The Egyptians achieved functionally equivalent decision-making quality with a stone column and a scribe. The data collection method was primitive. The data analysis methodology was not. Everything we have covered so far, the Basin system, the Shaduf, the Qanat, the clay pots, the nilometer data, these are not isolated curiosities. They are components of a single integrated philosophy of water management that treated every drop as irreplaceable. And what we are about to get into for the second half of this video goes even deeper. If the data we have covered so far has changed how you think about water and agriculture, and I genuinely hope it has, hit that like button right now. It tells us that this kind of deep historical analysis is what you want more of, and it helps us bring it to people who need to hear it. Subscribe if you want to be here every week when we go this deep into agricultural science and history, because what is coming next, the Sakya water wheel, the ancient soil amendment secrets, and the Kharga Oasis discovery that had hydrologists questioning everything they thought they knew, that is where this gets extraordinary. Do not leave now. If the Shaduf was the precision tool for small-scale water lifting, the Sakya was the industrial solution, and it represents a quantum leap in ancient irrigation engineering that allowed Egyptian agriculture to scale in ways the Basin system alone could never achieve. The Sakya, sometimes called the Persian wheel, though the Egyptian adoption dates to at least the 4th century BCE during the Ptolemaic period, is an animal-powered water wheel that uses a continuous chain of clay pots or wooden buckets attached to a large rotating wheel. An ox or donkey walks in a circle, turning a horizontal gear that meshes with a vertical gear that rotates the pot chain. As the chain rotates, pots dip into the water source, fill, rise to the top of the wheel, and tip their contents into a trough that feeds the irrigation channel. The mechanical efficiency of the Sakya is remarkable for a technology without metal gears or precision machining. A single ox-powered Sakya can lift approximately 20 to 25 cubic meters of water per hour to a height of 3 to 4 meters, enough to irrigate approximately 2 to 3 hectares of crops per day. For comparison, a man operating a Shaduf can lift approximately 1 cubic meter per hour. The Sakya multiplied human irrigation capacity by a factor of 20 to 25. The Sakya also introduced something conceptually important: continuous flow irrigation. The Shaduf operated in discrete lifts: fill, lift, pour, repeat. The Sakya operated continuously, delivering a steady stream of water that could be distributed through a network of channels with much greater precision and consistency. This allowed Egyptian farmers to irrigate larger areas with more uniform water distribution, a prerequisite for scaling agriculture beyond subsistence level. A 2022 engineering analysis published in the Journal of Water History modeled the aggregate water lifting capacity of the Sakya network in the Fayum Depression during the Ptolemaic period, approximately 300 BCE to 30 BCE. The researchers estimated that the region contained between 1,200 and 1,800 operational Sakyas during peak agricultural production, collectively lifting enough water to irrigate approximately 120,000 to 150,000 hectares, an area roughly the size of modern London. That is not primitive farming. That is industrial-scale water management achieved with wood, clay, rope, and animal power. And it was operating continuously for centuries before the Roman Empire reached its peak. The lesson for modern dry climate agriculture is not to replace electric pumps with ox-powered wheels. The lesson is the engineering philosophy: use the simplest possible mechanism that achieves the required result. Every layer of complexity in a modern irrigation system is a potential failure point, a maintenance cost, and an energy expense. The Sakya had 3 moving parts. It ran for decades with basic maintenance. In a world where energy costs are rising and climate instability is increasing, that philosophy deserves serious reconsideration. This section is where the story gets genuinely surprising, because what Egyptian farmers were doing to their soil, without any knowledge of chemistry, microbiology, or plant nutrition science, turns out to be almost perfectly aligned with what modern soil scientists now consider best practice for arid climate agriculture. The Egyptians were not just using the Nile flood for water. They were using it as an annual soil amendment delivery system, but they also supplemented it with practices that, when analyzed through a modern lens, reveal a sophisticated empirical understanding of soil health. The first practice was the deliberate incorporation of sebak, a term referring to decomposed organic material found in ancient settlement mounds. Egyptian farmers throughout history have mined ancient tells, the mounded ruins of old settlements, for their soil, which they spread on agricultural fields. This practice, documented in agricultural records from the 19th century, but almost certainly much older, was so widespread that it actually destroyed many important archaeological sites. Why did it work? Because ancient settlements were essentially composting systems. Centuries of human occupation deposited organic waste, Food scraps, animal dung, ash, and decomposed building materials, mud brick made from Nile clay and straw, into a concentrated layer that was extraordinarily rich in nitrogen, phosphorus, potassium, and beneficial soil microorganisms. Spreading sebakh on agricultural fields was functionally equivalent to applying high-quality compost, and the farmers who did it observed better yields without understanding why. A 2020 geochemical analysis published in Journal of Archaeological Science measured nutrient concentrations in sebakh samples from multiple Egyptian sites and found total nitrogen concentrations of 0.22 to 0.31%, significantly higher than typical agricultural topsoil and comparable to commercial compost. The second practice was the strategic use of green manures. Egyptian agricultural texts from the Middle Kingdom period and approximately 2000 BCE describe the plowing under of specific plants, particularly fenugreek and clover, before planting grain crops. The Egyptians observed that fields treated this way produced better yields. They attributed it to spiritual or magical properties. Modern agronomy attributes it to biological nitrogen fixation, the process by which leguminous plants like fenugreek and clover harbor rhizobium bacteria in root nodules that convert atmospheric nitrogen gas into plant-available ammonium compounds. Fenugreek, Trigonella phoenum graecum, can fix between 50 and 150 kilograms of nitrogen per hectare per season when properly inoculated with rhizobium bacteria. The Egyptians were applying the equivalent of 50 to 150 kilograms of synthetic nitrogen fertilizer per hectare for free by growing and plowing in a plant they considered to have magical properties. The magic was real. They just had the wrong explanation for why. If you want to understand the full ambition of ancient Egyptian water engineering, you need to understand the Fayum Depression. Because what Egyptian engineers accomplished here, beginning around 2300 BCE under the 12th dynasty pharaohs, is arguably the most audacious agricultural engineering project of the ancient world. The Fayum Depression is a natural geological basin located approximately 90 kilometers southwest of Cairo. It sits below sea level, at its lowest point, approximately 43 meters below the Mediterranean. In its natural state, it was a vast desert basin with a shallow, highly saline lake fed by a seasonal connection to the Nile. Egyptian engineers transformed it into the most productive agricultural region in the ancient world. The project involved excavating and maintaining a major canal, the Bahr Yusuf, or Canal of Joseph, that diverted Nile floodwater into the depression during high flood season and controlled its drainage during low season. By regulating water input, engineers gradually reduced the salinity of the lake, reclaimed the surrounding basin margins for agriculture, and created a controlled irrigation system covering approximately 450,000 fedans, roughly 189,000 hectares. The scale of this achievement requires context. The Hoover Dam, completed in 1936, irrigates approximately 405,000 hectares in the American Southwest using hydroelectric power, concrete, and steel. The Egyptians irrigated nearly half that area using earthen canals, wooden sluice gates, and human labor, and their system ran continuously for over 2,000 years before the Romans inherited and expanded it. The Fayum project also demonstrated something critical about Egyptian engineering philosophy. They thought in centuries, not seasons. The initial excavation of the Bahr Yusuf Canal was begun under Amenemhat I around 1990 BCE and expanded under Amenemhat III around 1800 BCE. A project spanning approximately 200 years and multiple pharaonic administrations, each generation built on the previous one's work, improving the system incrementally based on accumulated observational data. A 2019 remote sensing study published in Remote Sensing used satellite imagery and LiDAR data to map the surviving traces of the ancient Fayum Canal network. The researchers identified over 1,200 kilometers of ancient canal traces in the depression, a hydraulic network of extraordinary complexity and precision built without GPS, without aerial survey, and without any of the tools we consider essential for large-scale water infrastructure. The Fayum Depression today still produces some of Egypt's most productive agricultural land, still irrigated in part by the Bar Yusuf Canal, the same canal that Egyptian engineers began digging 4,000 years ago. That is the definition of sustainable infrastructure. Endadion. This is the section I promised you at the beginning, the 2017 discovery at the Kharga Oasis, and it genuinely does rewrite what we thought we understood about ancient water management in desert environments. Kharga is Egypt's largest oasis, located approximately 200 kilometers west of the Nile in the western desert. It has been inhabited and farmed for at least 3,000 years, sustained by a remarkable ancient Qanat system that taps the Nubian sandstone aquifer, one of the largest known fossil water reservoirs on Earth, containing an estimated 150,000 cubic kilometers of water accumulated during the last wet period of the Sahara, approximately 10,000 years ago. In 2017, a joint research team from the University of Oxford and the Egyptian Antiquities Organization conducted a systematic survey of the Kharga Qanat system using ground-penetrating radar, satellite imagery analysis, and physical excavation of selected sites. What they found was published in the Journal of African Archaeology and immediately attracted attention from water engineers and hydrologists worldwide. The team discovered that the ancient Qanat engineers at Kharga had incorporated a feature into their system that modern hydrological theory would not formally describe until the 1960s: deliberate aquifer recharge zones. Specifically, they found that certain Qanat tunnels had been deliberately widened and their floors lowered at specific points along their length, creating underground chambers that filled with water during high-flow periods and slowly released it back into the surrounding aquifer during low-flow periods. The ancient engineers had built underground reservoirs directly into the aquifer system, using the aquifer itself as a storage medium. This is precisely what modern water engineers call managed aquifer recharge, a technique considered cutting-edge in contemporary hydrology, involving the deliberate injection of water into aquifers to supplement natural recharge. The Kharga Qanat engineers were doing this 2,000 years ago, not with injection wells and pumps, but with shaped underground chambers and gravity-fed water management. The Oxford team's lead hydrologist, Dr. Nick Drake, was quoted in The Guardian following the publication as saying, "We are looking at an ancient water management system that shows a level of hydrological understanding we would not have credited to engineers of that period. Some of what they built, we are only now developing the theoretical framework to fully explain." Let that sit with you for a moment. We are only now developing the theoretical framework to explain what they built 2,000 years ago. We are in the final stretch of this video, and what is coming in the last two sections is where everything we have covered converges into something that should genuinely change how you think about agriculture, technology, and the relationship between ancient knowledge and modern practice. If you have made it this far, and the fact that you are still here tells me something about you. You are the kind of person who actually wants to understand the deep mechanics behind why things work, not just the surface-level story. That is exactly what we do here every single week. Subscribe so you are here for the next one, because we are going deep into ancient Mesopotamian soil science next, and the data from that one is even more surprising than what you have heard today. Now, let us talk about what happens when modern science actually tries to replicate these systems head-to-head. For the past decade, a growing number of agricultural research institutions have been doing something that would have seemed eccentric 20 years ago, running rigorous controlled trials that directly compare ancient Egyptian and Middle Eastern irrigation techniques against modern technology in arid and semi-arid conditions. The results have been, depending on your perspective, either deeply humbling or deeply exciting. Let us go through the key studies, because the data tells a story that no amount of narrative framing can improve. The most comprehensive comparison study to date was conducted by researchers at the International Water Management Institute, IWMI, and published in Agricultural Water Management in 2022. The study ran across 3 sites in Morocco, Jordan, and Tunisia over 2 growing seasons, comparing 5 irrigation methods for tomato and pepper production. conventional surface irrigation, modern drip irrigation, subsurface drip irrigation, clay pot irrigation, and reconstructed basin percolation irrigation. The metrics measured were water use efficiency, crop yield, soil electrical conductivity, a measure of salinity buildup, and soil microbial biomass. Water use efficiency, kilograms of crop produced per cubic meter of water applied. Conventional surface irrigation, 3.2 kilograms per cubic meter. Modern drip irrigation, 6.8 kilograms per cubic meter. Subsurface drip irrigation, 8.1 kilograms per cubic meter. Clay pot irrigation, 9.4 kilograms per cubic meter. Reconstructed basin percolation, modified for small-scale use, 7.2 kilograms per cubic meter. Clay pot irrigation outperformed even subsurface drip irrigation, the most advanced modern system tested, by 16% on water use efficiency, and it did so at a fraction of the capital cost. But the soil health data was even more striking. After 2 growing seasons, soils under clay pot irrigation showed microbial biomass carbon concentrations of 412 micrograms per gram, compared to 287 micrograms per gram under drip irrigation and 198 micrograms per gram under surface irrigation. Clay pot irrigation produced 63% higher soil microbial biomass than modern drip irrigation. Why does this matter? Because soil microbial biomass is the single best predictor of long-term soil fertility and agricultural sustainability. Soil with higher microbial biomass requires less external fertilizer input, resists erosion better, sequesters more carbon, and maintains fertility over longer periods. The clay pot system was not just using less water, it was actively building soil health while the drip system was degrading it. The salinity data told a similar story. After 2 seasons, soils under drip irrigation showed electrical conductivity of 3.8 decisiemens per meter, approaching the threshold where salt stress begins to reduce yields in sensitive crops. Clay pot irrigated soils showed 1.9 decisiemens per meter. The ancient system was preventing the salt accumulation that is one of the most serious long-term threats to irrigated agriculture in dry climates. This is not a small difference. This is the difference between a field that is productive in 50 years and one that is not. We have spent nearly 30 minutes going through the mechanics, the data, the engineering, and the science. But I want to end somewhere different. Because the most important thing ancient Egyptian irrigation teaches us is not a technique, it is a philosophy. And it is one that modern agriculture has almost completely abandoned. The Egyptians operated under a constraint that modern irrigated agriculture does not acknowledge. The water they had was the water they had. There was no deeper aquifer to tap when the surface supply ran low. There was no dam to build to store more than the river provided. There was no desalination plant to manufacture additional supply. The Nile gave what it gave, and the entire civilization had to work within that constraint or collapse. And so they built systems that were optimized not for maximum extraction, but for maximum efficiency within a fixed supply. Every technique we have discussed, basin irrigation, clay pots, Qanats, sakyas, green manures, Sebek amendment, shares this fundamental characteristic. They do not try to supply more water than the environment provides. They try to use every drop of available water with maximum effectiveness. Modern irrigated agriculture has taken the opposite approach. Global groundwater withdrawals for irrigation have increased by 800% since 1950. The Ogallala Aquifer beneath the American Great Plains, which took approximately 6 million years to fill, is being depleted at a rate that will make it non-viable for irrigation within 50 years at current withdrawal rates. The Indus Basin Aquifer System, which supports agriculture for 300 million people in Pakistan and India, is losing approximately 27 cubic kilometers of water per year, more than natural recharge can replace. The Aral Sea, once the world's 4th largest lake sustaining a fishing industry that employed 60,000 people, has lost 90% of its volume since 1960, almost entirely due to irrigation withdrawals from its feeder rivers. It is now a toxic salt flat. That happened in 60 years. The Egyptian basin system ran for 3,000 years without degrading its water source. The question is not whether ancient Egyptian techniques are romantically appealing. The question is whether the philosophy that produced them, the philosophy of working within the boundaries of what the environment provides rather than extracting beyond those boundaries, is one that modern agriculture can afford to ignore. A 2023 report from the United Nations Food and Agriculture Organization estimated that 40% of the world's irrigated agricultural land is experiencing some degree of soil degradation from waterlogging, salinization, or nutrient depletion, all consequences of irrigation systems optimized for maximum water delivery rather than maximum water efficiency. The report estimated that restoring this degraded land would require between $1.4 and $2.1 trillion of investment over the next 30 years. For a fraction of that cost, we could be teaching farmers in arid regions to build clay pots, excavate Qanats, and design basin irrigation systems. We could be applying 3,000 years of empirical knowledge that has already been validated by modern science. We could be choosing efficiency over extraction, patience over speed, and long-term productivity over short-term yield maximization. The Egyptians did not have a choice. They had to get it right, or the civilization ended. We have a choice. And right now, most of the world's agricultural systems are making the wrong one. That is the thing about ancient knowledge. It does not just tell us what worked in the past. It tells us what we are risking by forgetting it. We started this video with a question. How did a civilization of 5 million people survive in one of the driest places on Earth for 3,000 years? And now you know the answer is not simple. It is not one technique or one invention. It is a coherent philosophy of water management built from centuries of empirical observation that treated every drop of water as irreplaceable and every acre of soil as a long-term investment. The Basin system, the Shaduf, the Qanat, the clay pot, the nilometer, the sakia, the sebak, the green manures, the Fayum project, the Kharga aquifer recharge chambers. None of these are primitive. All of them have been validated by modern science, and most of them outperform modern equivalents on the metrics that matter most in a world where water is becoming the most valuable resource on Earth. The one sentence I want you to carry out of this video is this: the most sophisticated water management system in history was built from earth, clay, and patience, and it outlasted every empire that tried to improve on it. If this changed how you see ancient knowledge, and I genuinely hope it did, share this video with someone who needs to hear it. A farmer, a gardener, someone who thinks technology is always the answer. This is the kind of information that should not stay in academic journals and archaeology reports. It belongs in the conversation about how we feed the world through the next century of climate change. And if you want to go deeper on the ancient agricultural systems that modern science keeps rediscovering, the next video is waiting for you right now. The Mesopotamian soil science techniques that produced yields modern organic farmers cannot match. Click it. You will not regret it. If the Egyptian water engineering in this video fascinated you, you absolutely need to see our breakdown of Mesopotamian agricultural science, the civilization that invented crop rotation, companion planting, and soil amendment records 2,000 years before Europe discovered them. It is linked right here. See you in the next one.